Hello guys, welcome to our 10th lecture on our course on photonic devices. On today's lecture we are going to talk about the carrier density, the law of mass action, and we're going to define expressions for the Fermi levels. As a recap, we have seen in our previous lectures that the electron carrier concentration in the conduction band and the hole carrier concentration in the valence band are calculated by these expressions. So you need to integrate over the entire energy range related to the band this integrand, which is the density of states. Okay, so the more states you have per unit energy, the more carriers you have, multiplied by the probability of occupation. Now, in the case of electrons in the conduction band, this is the probability of occupation of electrons, which is the Fermi function, the Fermi distribution. And for holes in the valence band, you multiply the density of states, of course, by the probability of occupation of holes, which is 1 minus the probability of occupation of electrons. And of course, you're integrating this over energy values that are within the valence band, so this function is going to be integrated over this range as well. But this product inside the integral right here is what we call the carrier density. Okay, so if this is the carrier concentration, this is the carrier density, which is the number of carriers per unit energy. In other words, if the carrier concentration is the total number of carriers in the band, in the conduction band in this case, the carrier density is the amount of carriers per unit energy. Okay, N of E, and it's a function of E. Now this is for electrons, and of course you have P of E, the whole carrier density for holes in the valence band. Okay, same thing, amount of carriers per unit energy as a function of E. So it's the product, the carrier density is the product of the Fermi function and the density of states. And therefore, as we move from the border or the edge of the conduction band or the valence band towards the center of these bands, the number of states grow, the density of states grows, right? So let's draw the band structure here again. Start talking about the conduction band, and then we'll talk about the valence band. But for the conduction band, if we draw the corresponding density of states, so rho of E, we saw that from the energy corresponding to the band edge, the density of states grows with the square root of E. So it would grow with a function that looked like this, right? This is the density of states. But the probability of occupation decays, in this case, with the Fermi function, with the Fermi distribution. Therefore, if we were to draw, the Fermi distribution, we saw that F of E looked something like this, right? In the valence band, it was close to 1, and then it decayed down to 0, and it was right around here, halfway in the middle of the band gap, but it decayed to 0 towards the conduction band. Since the carrier density N of E is the product of these two things, right? It's the product of the density of states, rho of E, and the Fermi function, F of E, then the carrier density is going to look something like this. It's going to be the product of the green function and the red function, and therefore it's going to look something like this, right? What I'm drawing in purple right here would correspond to the carrier density N of E. And you would have something similar in the valence band, right? Except that in the valence band, the probability of occupation of holes is 1 minus F of E. So let's try to draw this here. So now we're talking about the valence band. Okay, so for valence band energies, you have the EV, the band edge right here. And if we again draw the density of states, okay, so let's draw rho of E for the valence band now. So this corresponds to rho of E for the conduction band right here. It still grows with the square root of E towards the center of the valence band as well. So it looks something like this similarly. And we can also draw the probability of occupation, but now for holes, which is 1 minus the Fermi function. So if it's 1 minus this, well, let's see, right here, it would be 1/2, right? And we're drawing the probability of occupation 1 minus f of E now. So the probability of occupation for holes, it's half right here, and it is, whereas f of E is 1 here, it's going to be 0 here. So it's 0 here, and then it grows up to half, and then it is close to 1 in the conduction band, right? So it would grow like so, something like this, right? It's 1 here and around half here for an undoped semiconductor. And again, if we multiply the probability of occupation for holes by the density of states, we get the carrier density, which looks like the product of the green function and the red function, giving us the purple function right here. Right, this function is now P of E, the whole carrier density. Okay, it's a product of the red and the green functions. So what we see here is that the electrons are concentrated close to the band edge with a peak that is slightly above the band edge for the conduction band. And the holes, on the other hand, so the electrons are concentrated right here, and the holes, on the other hand, are concentrated near the band edge of the valence band. Again, with a peak that is slightly below the band edge EV. Now let's see how the carrier density looks for doped semiconductors. So on the left here we have the Fermi distribution for an N-type semiconductor and the Fermi distribution for a P-type semiconductor. So the blue curves correspond to the density of states, right, in the conduction and the valence band, and the full red line corresponds to the Fermi function. So as we saw, in an N-type semiconductor, the Fermi level is closer to the conduction band than to the valence band, and the Fermi function is displaced toward this direction. So it's displaced up in the band diagram. For a P-type semiconductor, the opposite occurs. The Fermi function and the Fermi level are displaced down towards the valence band. We also see here in dashed red the probability of occupation of holes, which is 1 minus the probability of occupation of electrons. So the dashed red curve is 1 minus the full red curve right here. Okay. Now, for an N-type semiconductor, since the Fermi function is displaced towards the conduction band, when you take the product of the Fermi distribution by the density of states in the conduction band, you get this, which I'll draw in green here, something like this. And this is now N of E, okay, the carrier density N of E. And if you take the product of the probability of occupation for holes, which is the dashed curve here, by the density of states in the valence band, you get something much smaller, right? Because the probability of occupation for holes in the valence band for an n-type semiconductor is much smaller, reflecting the fact that you have fewer holes here. So you get something much smaller here, okay, which I'm trying to illustrate here. So if you compare this to this, you see that in the n-type semiconductor you have a carrier density of electrons which is much larger than the carrier density of holes. Okay, but they're both the product of the probability of occupation for the respective carrier by the density of states. Okay, now if we talk about the p-type semiconductor and we multiply the density of states in the valence band by the probability of occupation for holes, which we see that is, displaced down as we've said, you get a carrier density P of E, which is large. So P of E is large here as it should be. You have more holes. It's a p-type semiconductor with acceptor impurities which introduce holes into the semiconductor. And if you take the product of the Fermi distribution by the density of states in the conduction band, now you get something small here. Okay, so N of E is small in the conduction band for a p-type semiconductor. So in the p-type semiconductor you have a lot of holes. In an m-type semiconductor you have a lot of electrons in the conduction band. Holes in the valence band and electrons in the conduction band. If in order to find the carrier concentration N, for example, you need to integrate the carrier density N of E, okay, as we've just said, you need to do this for electrons over energies in the conduction band, so from EC towards infinity, then this means that the area under these curves that we have just drawn here is the carrier concentration. Okay, if this area is proportional to the actual amount of electrons or the amount of carriers, because since you need to integrate, this corresponds to the area under the curve. The actual area of these curves that we illustrated is proportional to the carrier concentration. The curves themselves correspond to the carrier density N of E, but if you integrate, you get the carrier concentration. Therefore, the area is proportional to the carrier concentration, which, as we've seen, is the amount of carriers per unit volume. Now, in our last lecture, we found analytical expressions for the carrier concentrations for electrons and holes, and this was done under the Boltzmann approximation. So let's recall that, the Fermi function f of E is actually equal to 1 over E to the power of E minus EF divided by KT plus 1. But if the Fermi level is not too close to either band edge, then this quantity is much larger than 1, and therefore this can be approximated by this expression right here. Okay, 1 over E to the power of E minus EF divided by KT. And you can ignore the 1 here, and this can be done as long as the semiconductor is not too heavily doped. The amount of dopant is not too large, okay? But under these conditions, these expressions were found. So the carrier concentration is the product of a constant times the exponential e to the power of E minus EC minus EF divided by KT. Same thing goes for the whole carrier concentration. It's the product of another constant NV times e to the power minus EF minus EV divided by KT. Okay, where these constants are given here. Okay, so they're a function of the effective mass, the temperature, and Planck's constant. Now, if you multiply these two things, you'll have NC times NV times the two exponentials, right? So you get this part, NC times this term, originated from the electron carrier concentration, and NV times this term originated from the hole carrier concentration. So some things cancel out here, right? Here you have e to the power of minus EF, which is equal to e to the power of EF. And here you have e to the power minus EF. So this cancels this out. And then it turns out that you have NC times NV, right, times e to the power minus EC over KT multiplied by e to the power of plus EV divided by KT, which is equal to NC times NV multiplied by e to the power of minus EC minus EV over KT, right? And therefore, you can substitute this by the band gap energy, right? E.g., EC minus EV is equal to the difference between the conduction band edge energy, the difference between this and EV, the valence band edge energy, which is exactly equal to the band gap, okay, the forbidden band gap energy. Therefore, you get this result, and let's keep this result in mind. Now, for an intrinsic semiconductor, we can state that the electron carrier concentration is equal to the hole carrier concentration, and this will be called the intrinsic carrier concentration, Ni. Why are these things equal? Well, if you consider the band diagram, right, you have the valence band and the conduction band. Fermi level is exactly halfway between these two bands, and for each electron that transits from the valence band into the conduction band, leaving behind a hole, you will have a one-to-one correspondence, because for each electron created, you have a hole that is automatically created as well. And when they recombine, the electron is no longer in the conduction band, but it cancels out the hole in the valence band. So for an intrinsic semiconductor that you have not doped, a non-doped semiconductor, the carrier concentration for electrons and holes is the same, and this will be called the intrinsic carrier concentration, Ni, okay, for an intrinsic material. And if we substitute this in 1, what we get is, so let's recall that 1 was N times P is equal to NC times NV times e to the power minus EG over KT. So we had this. Now, for an intrinsic material, both N and P are going to be equal to Ni, so this will turn out to be Ni squared. Okay, so for an intrinsic material, you have this equality, which is holding. Now, we have to notice that this expression is independent of the Fermi level. It's not dependent on EF. And therefore, Ni squared is going to be independent of EF. Also, expression number 1 was valid for a P-type and N-type semiconductor. And expression 2, which is this, is valid for an intrinsic material. So, since these two things are the same, then we can conclude that for any semiconductor, we must have N times P equal to Ni squared. Okay, so since 1 was valid for even for doped materials, this has to be valid as long as the Boltzmann approximation is valid. Then for any semiconductor, and here we include doped semiconductors, you must always have N times P equals to Ni squared. In other words, even for a doped semiconductor, the electron carrier concentration times the hole carrier concentration has to be equal to the intrinsic carrier concentration squared. Okay, and this is the carrier concentration for an intrinsic material. But these two do not have to be. So for a doped semiconductor, the product of the electron and hole concentration is always equal to the intrinsic carrier concentration, which is sometimes called the law of mass action, and we have to recall that it's only valid under the Boltzmann approximation. Okay, the product of the number of electrons in the conduction band and holes in the valence band is independent of the amount of donor and acceptor impurities added. So this product will always be the same and be equal to Ni squared. The intrinsic carrier concentration depends only on Eg, the temperature and the effective masses. So this comes about from this expression which you got right here, right? Ni squared is equal to Nc times Nv times e to the power minus Eg over Kt, which gives rise to this. Ni is equal to the square root of Nc times Nv times e to the power minus Eg over 2Kt. Okay, so the intrinsic carrier concentration is only dependent on the effective masses which go inside the constants Nc and Nv, and the band gap energy as well as temperature. So here we have a table for different semiconductors of interest such as gallium arsenide, indium phosphide, and silicon, of the band gap energy in electron volts, which we have already seen, the constants Nc and Nv, which are around 10 to the 17th to 10 to the 19th, and the intrinsic carrier concentration, which is smaller for gallium arsenide, which is a wider band gap semiconductor. So since it's a wider band gap semiconductor, you would expect that in an intrinsic material you'll have less electrons and less holes because they have to overcome a larger gap energy, right? So 2.5 times 10 to the 6th, whereas in silicon you have 1 times 10 to the 10th, so 4 orders of magnitude larger because the band gap is somewhat smaller, okay? And indium phosphide is somewhere in between.